Thank you everyone for waking up in the morning. I understand why Sergio is not here. To maintain commitment power, that is important. Okay, so I'm going to talk today about a literature that's, I guess, already a bit more than 10 years old at this point. I call it revenue maximization from samples. Some people call it, even I called it at some point, empirical auction design. Some people call it automated auction design. So it goes by many names. I'm not sure there's one. I think that if you stick samples in it, people understand what you mean, but there are various names. So here's the thing. You know, we now have internet scale marketplaces, Facebook, Bing, Amazon, whatever. To some extent, now is a time at which microeconomic theory should shine more than ever before. Because if you take a look at the ad auctions, these are the auctions that you see on a web page when it loads or after you search for something on Google. The ads that you see there. The literature tells us exactly how to maximize revenue, at least in some settings, if we fully know the market distribution. If we have a perfect prior over the buyers, the searchers, the browser, the people who browse the web. And yet, even Google or Facebook, with lots of past data, even if they're the best in the world at cleaning data, at most, they even if you take this frequentist approach that there even is a stationary distribution underlying the market, they do not know this distribution. At best, they see many samples from it. And the question is, you open your favorite microeconomic theory textbook, and as of at least 10 years ago, it didn't exactly tell you what to do if you only have samples from this distribution rather than this distribution perfectly. And the question we're going to ask today and tomorrow is, can the seller make do with samples? And more specifically, we're going to say, sure, we need a lot of samples, but not an exorbitant amount of samples. We'll formalize this soon. I'm presenting this as if it's a very new thing, but the sources of the discomfort with a perfect prior, of course, go way back to Wilson, even to Hurwitz to some extent. And Wilson, Bob Wilson in '87, in a paragraph that has become known as the Wilson Doctrine, tells us game theory has a great advantage in explicitly analyzing the consequences of trading rules that presumably are really common knowledge. It is deficient to the extent it assumes other features to be common knowledge, such as one agent's probability assessment about another's preferences or information. Exactly, a seller having a perfect prior over the buyer's preferences, for example. I foresee the progress of game theory as depending on successive reductions in the base of common knowledge required to conduct useful analysis of practical problems. Only by repeated weakening of common knowledge assumptions will the theory approximate reality. So what we're going to talk about today and tomorrow is one such weakening. Hopefully it will give someone in the audience the idea for the next weakening in this sequence of repeated weakenings that make this more and more applicable.
But his emphasis is on common knowledge. Your emphasis is on something else.
So,
because
if you're talking,
you realize that you don't have
yeah, but
objective
if
but
you
have
want
a certain assessment.
No, I agree. I agree that this is specifically about common knowledge. I think that the spirit here, though, is weakening knowledge assumptions generally, and specifically, if you think about, dominant strategy mechanism design, maybe that's less so. If you're thinking about Bayesian instead of compatible mechanism design, that's already, that I know that you know my prior over you or something. You need more levels there. But you're right. This is specifically about common knowledge. I'm taking this more in spirit. Just, my main point was, it's not that computer scientists at 2014 suddenly said, we're unhappy with priors. We're not the first to say that. That's my point. So, what do I mean by many samples but not an exorbitant amount of samples? Here we're going to take the computer science approach and we're going to say polynomially many samples in the number of items and the number of buyers and any parameter of the problem. That's many, but that's okay. Maybe Amazon has such many samples. Exponentially, that's too many. And one positive thing COVID has given us is that we all know that exponential is very, very bad and too big. So we all have internalized that.
And when you say polynomial and exponentially, what's the...
Well, I'll define that. As I said, in the parameters of a problem, whatever they may be. So we're going to work in a very, very standard setup. So we're going to have one seller, n items. So forget about Sergio's. Sergio's not here. Forget about Sergio's notation from yesterday. It's good notation. There's going to be. I'm going to try to match the literature of more than one author here. Yeah, no, I love Sergio. He was my advisor. He's fantastic. I think there's a lot of benefit to his notation. At this point, most of the literature uses a different kind of notation. So one seller, n items for sale, to n potential buyers. And we're going to do, very similar to what Sergio said yesterday. I's valuation for J is independently drawn from some distribution Vij. We're going to assume everything is bounded. I'm going to talk a little bit about unbounded. That has its own challenges in this literature, but already with bounded is interesting. Each buyer's valuation is additive across items, exactly like what Sergio did yesterday. It's a bottle and a clicker rather than a pair of shoes, where I value both of them more than the sum of each of them separately, and it's not a pair of cups where I actually do need only one. The seller wishes to find an auction mechanism, so there's a lot of argument about when is it an auction, when is it only a mechanism. I'm going to use these interchangeably throughout today and tomorrow. Apologies in advance to people who have a strong opinion about these. That would yield good revenue and expectation over this. So this is the revenue maximization problem that Sergio spoke about yesterday. And this mechanism must be individually rational and Bayesian incentive compatible. So my expected utility, if I bid truthfully, is weakly higher than my expected utility if I did something else. And there are two standard settings. One is the one Sergio spoke about yesterday. You might see it again in some other talks. Bayesian revenue maximization. The seller has complete knowledge of this underlying distribution from which buyers are drawn. I'm explicitly, and very intentfully taking a very frequentist approach, saying, buyers are drawn from this rather than this is a prior in the seller's head because of where we're going. And the other one is revenue maximization from samples. The seller has access to polynomially many samples. The polynomial is going to be in H and N and M and some other parameters we're going to throw into it soon. So polynomially many samples from this product distribution. And the question is, what can the seller do? But the benchmark remains the optimal auction given this. So the benchmark is exactly the same as Sergio's benchmark yesterday, but the seller has less information. This will obviously be a probabilistic statement. For whoever here is familiar with what's called pack learning in computer science, we're going to take a similar approach. Yeah.
So there's a specific set of buyers here,
Yeah.
potential buyers.
Yeah.
If there are many samples drawn, are we to think that it's the same buyers that are
So you can take various views on this. You can think about, you know, there are various populations, you know, professors and students and you know, non-tenured professors maybe is a different population. For each of these populations, you get, you know, that's one of the, you know, you can think about M as standing for populations. You get samples for each population. Then you run an auction. You're told, well, actually, you know, the people in the room now are 2 students, 3 tenure track faculty, and 2 junior faculty. That's one approach you could take. Another approach is you can think about the case of n equals 1. You know, that's essentially all that Sergio spoke about yesterday, and that's a very, very rich case. In that case, there is one distribution. You think about this as distribution for the entire population, and you're facing, you can think about facing either one buyer and that's it, or you can think about facing one buyer at a time. Maybe you're selling, you know, your Amazon Music, and you're selling a recording of something, so you sell each of it by itself. You don't have any supply constraints overall. You can take that approach as well.
But if the different buyers
Mm-hmm.
are distinguishable,
Mm-hmm.
if by some observable characteristics,
Mm-hmm.
then the optimal mechanism is going to exploit those characteristics.
Yeah.
So different, you're allowing for the possibility that different buyers will face different prices for the same thing.
For sure.
Yeah.
For sure. So yeah, so this can be any selling mechanism. You know, so this, I'm basically talking about the exact same problem Sergio spoke about yesterday. You can have 2 buyers, each coming from a different distribution, so you can totally price discriminate between them. The only difference is you don't know what the distribution is. You just have samples from that distribution. That's the only difference from the standard model we saw yesterday. Yeah.
I think yesterday we had dominant strategy instead of into the Bayesian one.
Yeah, so it's a bit different. Sorry?
How much does Bayesian give us?
So with one buyer, it's actually the same.
Okay.
Okay, so that's the thing you should bear in mind. When you have more than one buyer, what Sergio didn't do yesterday,
Yeah.
that's why he didn't have to define these differently. When you have more than one buyer, because like what's the expectation here? The expectation here is over the bids of everyone else. If there's no anyone else, this becomes a, you know, deterministic.
But why do
Or
you
at least
use
only expectation over the
Bayesian instead
randomness
of
of
dominant
mechanism.
strategy?
Sorry?
Why do you use Bayesian over dominant strategy?
Because I'm going to show you some results for Bayesian. Apparently, it turns out that some things you can do. Wait for tomorrow with that question.
Okay.
But it turns out that some things are more. I know how to do more elegantly with Bayesian instead of competitive. Yeah.
So basically, on the one hand, you say that there are no the seller is ignorant of the prior
Mm-hmm.
and is trying to learn them.
Mm-hmm.
On the other hand, they have very sharp beliefs about the prior that can be collapsed to a probability measure. So if it exists, right? So it seems like you're trying to tie 2 things that are a bit.
So let me ask you this: if you go to, I didn't have this slide here, but you know, say that I were to ask you, you know, in the standard econ literature, where does the buyer come from? Where does the prior come from? You're a seller. Where does your prior over the buyer's willingness to pay come from? You tell me, well, they're experts, they've seen many things, they have experience, etc., right? My claim is that if you model, not only my claim, you know, I didn't start this literature, but if you model, you know, this experience, or they've viewed many transactions in the past, or all this very carefully, it will boil down to they have seen many samples from some distribution from which they believe. You know, at least in the Amazon or Facebook case, you know, there are no experts there. It's a computer that has to decide how to price and when. What is it going based on? It's going based on past data. What can it go based on? You know what I mean? So it's one interpretation of where that prior might come from. I agree it's not the only interpretation, but it seems to be it's one interpretation over where the prior might come from, and it says, well, in that case, it's not, you know, there is a gap here that is worth discussing. It's fine to disagree. It's okay.
Can I ask you?
Yeah.
So, if the seller learns from the samples,
Mhm. Yeah.
the buyers anticipate them,
Yeah.
that can
Okay,
manipulate.
okay, good. So note that it never did, I was very careful, even in the examples that I gave Eric, to say, you know, you're facing buyers from populations, or you're selling a music track, you know, one person time to many people from a specific population. I was very careful not to use an example in which you face the same buyer twice.
Mhm.
So we're gonna assume that buyers, it's an implicit assumption, but you know, as I said in the beginning, we're gonna assume that you have clean samples, whether because you have fantastic I/O abilities or whatever. There is literature that I will not touch upon today that's, you know, less, you know, you see samples, but more, you know, you can run a mechanism many times and tweak it as you go along, and from previous bids you learn about the future, and some buyers may not be myopic. That's, you know, we need to learn to walk before we learn to run. But you're right, that's an interesting question. Yeah.
And do you require anything, like what power do you require from the buyers? Do you require them to know the whole,
We'll get to this. You're asking about BIC.
yes.
Okay, so we'll get to that, I think, tomorrow. Today will be more dominant strategy. Tomorrow we can have this discussion. Yeah.
I want to ask just whether the BAC is over the samples or for
So
the
so
realization
so
of the
let's
samples.
let's take both of these questions and leave them for tomorrow. Okay. So the standard setup that you all know is the seller, I'm saying is given. This is kind of a, you know, algorithmic point of view, but we can think about the seller as being given a distribution from which the buyer types are drawn, but not knowing the realization. And the goal is to find a truthful auction. Truthful could be dominant strategy or Bayesian, that maximizes the revenue of the seller in expectation over this distribution. So if you imagine the seller as an algorithm, the picture is there's this distribution, you feed it into the algorithm, you get the rules of an auction, and it should perform well over this distribution. Empirical auction design, or, you know, I told you this goes by many names, is you know, has a slightly more complicated picture. The seller is given polynomially many samples from a distribution from which the buyer types eigenvaluations are drawn, but does not know the distribution or the realization. So the picture is there's this distribution, we draw many samples from it, you know, it will be noisy, it will not tell us exactly what the distribution is. You feed these samples into some algorithm, and this algorithm should output the rules of an auction that should perform well over this unknown initial distribution.
What do you mean that he does not know the realization? I thought that that's exactly what he knows.
No. That it knows past realizations. It does not know the realizations over which the
okay.
auction will be
So
run.
you call those simple.
I call those samples and I call these realizations. Yeah, so like here it does not know the realization. Here it's they get samples, they still don't know the current realizations on which it is run. The goal is to find a truthful auction that maximizes asterisk, we'll get to the asterisk in a second, the revenue of the seller in expectation over this unknown distribution. And this asterisk, you know, is like the, you know, the disclaimer, may contain traces of nuts or whatever, up to an additive epsilon. Obviously you don't see the precise distribution, so you cannot optimize completely. And with high probability, you know, there is a very low probability that you'll get very, very, very unrepresentative samples. In that case, you have nothing to do. So we need to add these two disclaimers. And again, as I said in computer science, this kind of up to an epsilon with high probability is sometimes called PAC learning. PAC stands for probably, that's the high probability, approximately, that's the epsilon, correct. So probably approximately correct is one of the least scientific sounding, you know, terms I know of in computer science, but actually it's actually beautiful literature that goes back way, way before anyone thought about doing this with auctions. So what are the challenges? The naive approach, or the first approach. At least with actually ignore this parentheses, it's a leftover. Perform Bayesian optimization with respect to the empirical distribution over the samples. What do I mean? You get some samples. Take the uniform distribution over the samples. For the mathematicians here, want to be super, accurate. The uniform distribution over the multi-set of samples. Do, if it's one item, do Meyerson's optimization. If it's several items, do, whichever optimization you know how to do. We learned from Sergio yesterday that we don't know a lot, but do something that you know how to do. And get something and hope that it performs well over this distribution that lives here that we have not seen. The potential problem here is overfitting. That's something we encounter many times in statistical learning and machine learning. The problem is that we need to understand why or whether a mechanism tailored for a slightly noisy version of the true distribution can, whether it can conceivably perform very poorly on the true distribution, and at the very least, how can we make sure that it is not? That is the problem. The thing is that if, there are many, many degrees of freedom in choosing this mechanism, then, we might overfit as in any statistical learning problem. It's known that you have what's called the curse of dimensionality. That's generally speaking in machine learning and statistical learning. If you're tweaking many, many, many parameters, you might overfit to the specific samples. A standard approach in statistical learning theory or machine learning is, well, if we optimize over a low-dimensional family of hypotheses, in our setting, if we optimize over a low-dimensional family of auctions, maybe we won't overfit. So recall from yesterday, I think Sergio mentioned this, when there was one buyer. This is a beautiful theorem by Moshe, who's sitting here, and by Nicole Morlika, Brandon Lucier, and Matt Weinberg. When m equals 1, when there is only one buyer. And I'm phrasing it a bit differently than you would usually see it. There is either a separate item pricing mechanism or a bundle pricing mechanism that guarantees a revenue. The G4 of that mechanism, in Sergio's language from yesterday, is at least 1/6 of the optimal revenue. I'm phrasing it like this. Usually the way you would see it phrased is the maximum of the best separate item selling mechanism or the best bundle pricing mechanism will give you at least 1/6. I prefer to think about it this way, at least for this talk, because this means if we're lucky, and in some formal sense, the class of all separate item pricing mechanisms, union all bundle pricing mechanisms, has low dimension, then if we optimize over that class and find the best in that class, we will not overfit. So we'll be able to recoup this 1/6 guarantee, or close to it, 1/6 minus epsilon, also from samples. So this is going to be the first thing we try to do.
Does this theorem assume sampling, or not everything?
No, this is for a perfect prior. It will be our duty to adapt it to sampling.
Of course, that may not be considered a very ambitious goal.
I agree, and you're anticipating my next bullet, which is, I'm a computer scientist by training, so I'm allowed to ever so slightly bash computer scientists and say that, and this is not specifically about your paper. What I'm going to say now is about hundreds of papers by virtually every computer scientist in Econ CS that I truly admire. Many times you will see papers guaranteeing 1/6, 1/50, 1/100, and the abstract will say, we approximate the optimal revenue. For computer scientists, they know that when they say we approximate, they mean up to a constant, because what else is there when you talk about runtime complexity? And they're so used to thinking about, runtime complexity that what else is there remains when they move to approximating other things where this actually matters. So computer scientists in the audience, if you want to avoid economists getting a weird itch when they read your abstract, please do not say approximate the optimal revenue if you don't mean 99% or up to an epsilon or 80% or something along these lines. Yeah, so this, and indeed tomorrow we will talk about up to epsilon, but that's for tomorrow. We need to learn simpler things. But this actually, you know, it might sound like I'm just using this stage to bash where I came from, etc. That's not correct. Truly, if you want to talk across disciplines, it's a collection of many things. Each of them seems tiny to you, but overall they will make your message so much clearer to the audience that you want. So I highly encourage you to take note to these things. Try to read papers from the discipline to which whose audiences you aim, and take a look at everything that seems weird to you when you read that paper. If you write it the way you're used to, will seem weird to that audience. So that's a journey, but in my opinion, a one well worth taking. If we optimize, yeah, so the idea is, as we said, if we optimize only over separate item pricing and bundle pricing mechanisms, can we argue that since they are low dimensional, we need to define this, overfitting is ruled out, giving the same guarantee, you know, up to an epsilon? That's going to be the thing we're going to discuss today. And there are many learning theoretic off-the-shelf ways to formalize the idea of something, of some class of things you optimize over having low dimensionality. These include the pseudo dimension, Rademacher complexity, fat shattering dimension, among many others. So you know there are many options. There's no correct choice. Today we're going to talk specifically about the pseudo dimension. This is for whoever is familiar with the VC dimension. It's a real valued variant of the VC dimension. So if you're familiar with the VC dimension, you're going to have a less steep learning curve. And we're going to follow generally the analysis of a beautiful paper by Jamie Morgenstern and Tim Roughgarden from 2016. So the abstract setup is as follows. There is some unknown distribution V over Rn. I'm now in the business of defining to you the pseudo dimension, what it's good for. So, you know, I'm writing here in kind of light parentheses. You can think about these as evaluation distribution, that's fine, but this is actually more general than that. It's applicable to many other settings. There is a set A of functions from Rn to 0h. And the thing I'm going to ask you to think about here is the revenue functions of the mechanisms we optimize over. What do I mean by that? Each mechanism that you're considering, you know, it could be sell the first price for $3, the first item for $3, the second one for $5, the third one for $10, etc. Defines a revenue function. What's a revenue function? It's a function from the realized valuations to the realized revenue to the seller, or the expected revenue to the seller over the intrinsic randomness of the mechanism. This is the function I want you to think about. It's a function from R to the n, that's the space of valuations, to 0h. I'm lying a little bit, you know, the way I set it up earlier, the maximum revenue should be n times h, right? It can be maybe mn times h or something, right? Because if each item is valued by at most h, you know, but it's fine. Let's think for these slides about 0h. Observing samples from V, we wish to find a function. You know, I'm going to stop saying auctions now, but you have to set up in your mind if you want something concrete. We wish to find an auction that has almost maximum expectation over, sorry? Over V. This should say V. I'm sorry. Yeah. This is the distribution. So we have a distribution that we don't know. We see samples from it. Out of all the possible functions that we consider, we want to find the one that maximizes expected revenue over this distribution. Assume for a moment this will stop being true in a second, but as a, you know, as a warm-up, assume for a moment that this set that we maximize over is finite. This is obviously not going to be the case with, you know, continuous prices and whatever, but assume this for a moment. Then this turns out to be quite easy, and in fact something harder is already quite easy. So let's parse this theorem, and we're going to prove it soon. So there exists a constant C such that for every finite set A of functions that we're considering, and for every epsilon and delta, if we take so many samples from V, so many is, you know, this depends on H and epsilon and 1 over delta and on, you know, log of the size of A, then with probability at least 1 minus delta, we have that for every A, for every specific function, the empirical average and the theoretical expectation are very, very close. I will just say one thing, since, you know, in the same vein of talking a little bit about, give me 1 second, speaking between computer science and economics. Usually if a computer scientist were to write this, they were to start at this point. They would say for every finite set A and for every epsilon delta, setting S equals, at best they will say C times it's in this, at worst they will say big O of everything without the C or theta of everything without the C. And you will have to understand that C is a global constant, or maybe they will say for a global C, and you will have to understand that it doesn't depend on A and doesn't depend on epsilon and delta. I encourage you to write like this. Even actually if you write for a computer scientist, this is clearer. It's you know, I've seen very, you know, veteran computer scientists try to decipher statements with big O and theta for several hours, only to figure out that, oh, they actually meant something else and they missed something, etc., etc. So I encourage you to write clearly. You seem...
I disagree, yeah. I mean, there was a reason why people invented the big O notation, exactly to be able to get rid of that first part of the statement without annoying people.
So,
Rich people.
exactly.
Yeah.
So,
Anyhow, for an economist, this
for an economist, this is better. That we have a consensus on this. Very good. Okay. So let's prove this. It's a very simple proof. Some of you even see the proof. Yeah, sorry.
I need a step back.
Yeah.
Definition of A.
Yeah.
Is it like it's a function that just takes a valuation?
It's so you're talking about this grading. How do I interpret A?
Yeah,
Right.
what's
So this is weird because we're not used to thinking about auctions or about mechanisms like this. This is the function that takes a valuation and tells you, for this specific auction, on this specific valuation, what's the seller's revenue.
okay.
So if you're pricing one item at 3 and one item at 5, for the valuation 9.9, it's going to be 3 plus 5 because you sold both of them. For the valuation 4.0, it's going to be just the 3 you didn't sell the
So
5.
A is fixed not only for the valuation, but for every auction that
Every auction has its own A.
Okay.
This is the set of revenue functions of mechanisms. Each mechanism has its own revenue function.
Okay, now I
Single agent?
Sorry?
Single agent mechanisms with multiple items, or
You
this
can-
is n agents or the number of items?
This can be R to the n times m in the pre. I didn't want to, you
Okay.
know, do n times h
But
here
we
and n
should
times
think
m
of it
here.
as,
Yeah, it can be.
both
You
n
can
and
think
m.
about it completely generally. Yeah.
So, is it equivalent defining an option like this then through, you know, like a buyer side allocations and the payments?
So you know, this is a general tool. You can apply to many things. I'm curious about what you want to apply it to on the other side, but I'm going to ask you to, let's maybe take this offline. Yeah.
Just before we continue on to the proof, just to make sure we're on the same page. So this is sort of like a law of large numbers for these options.
Yeah. And this is really how we're going to prove it. So fix some revenue function of a specific auction by the Chernoff-Hofstadter Hefting bound we have for every choice of S. So we need to find the correct S, right? So we're thinking if we take 5 samples or 10 or 20 or 30, what will happen? So we're starting with, we're asking ourselves, when will the bad event happen? When will this difference be more than epsilon? So this difference being more than epsilon means that the difference between the sum of expectations and the sum of what we've seen is greater than S epsilon. By Chernoff-Höfting or Azuma, if Sergio were in the audience, he would say, why do you say Sergio Höfting? Everything is a special case of Azuma, so if you know the Azuma inequality, you can do that. This is less than or equal to what Chernoff-Höfting tells you. We're going to want this probability, the probability of the bad event, not to equal delta, but to equal delta divided by the size of the set calligraphic A. So this gives us the S that we want. And since for every auction separately, the bad event of this not holding holds the probability D over size of A, we take a union bound and the theorem holds. It means that with probability 1 minus delta, none of the bad events happen. Okay, this kind of Chernoff union bound, I don't know, a third of the papers in theoretical computer science, someplace throughout the paper have, let's do Chernoff then union bound. This is a very common technique. So this basically says for a finite set, for each A separately, I take enough samples so the probability for it is super, super small, and you know, even if I compound the errors, everything is fine. The question is, how does this help us? Say again still that the set was A. Our goal was not to estimate the revenue for each of these. Our goal was to find one that is approximately optimal. So here it's, you know, you can imagine how we're going to continue. We're going to draw this number of S samples. We're going to call capital AS the empirical revenue maximizing mechanism, the mechanism that maximizes revenue over the empirical distribution. We're going to call A capital V the truly optimal mechanism that we do not know. And then with probability at least 1 minus delta, this thing holds. And we can say that the expected revenue from the empirical maximizer is very close to the empirically estimated revenue. And this is greater or equal to the empirical estimated revenue from the actual true mechanism. Why? Because we chose this to maximize the empirically estimated revenue. And again, by this theorem, one more time, we'll lose another epsilon by switching back to expectations. So this tells us that with high probability, the empirical revenue maximizing mechanism maximizes expected revenue over V up to 2 epsilon. In other words, no overfitting. Yeah?
Is there a version of this result that doesn't rely on the IID assumption?
Yes. Yes.
And then just the bounds are a bit...
Yeah, so independent and not IID is fine. You can adapt it the way, you know, same proof mutatis mutandis. Without independence of the samples, no, actually, sorry, I take it back. Which independence are you talking about?
So, for example, I may not, I may assign some belief that my samples are correlated.
Okay, good. So, I'm assuming there is. I don't know how to tell you off the top of my head. I thought for a minute what confused me, I thought you meant, so one thing I should say, this V, as we said, you know, each sample here is a tuple of evaluations. If you think in the Oxford interpretation, it's tuple evaluations for every buyer and every item. We do not at all use the independence there. We only use the independence between the samples. That's what threw me off in the question.
Basically, you need the law of large numbers. Whenever you get the law of large numbers, whatever
Yeah.
correlation is good enough to not destroy the law of large numbers.
And if you have a very good law of large numbers, fine. If you have a weaker one, so like the optimal thing to use for every specific kind of correlation, ask you. Yeah, you're a statistician. That's
Yeah, it's true, but if you,
yeah,
there are versions that we can sufficiently.
yeah. So ask your local statistician regarding your specific assumptions. Yeah.
So in which step do you need to find that step for the proof?
So for the proof, we divide here by the size of A. Okay, that's the only place. And it's actually important that in everything I did here, I didn't use finiteness. So if I had a version of this theorem that didn't say finite, this would still hold. So, and indeed, the problem is finite here. The problem also in the number of, samples, you see that this explodes.
And this simple number does not depend on the dimension of the dimensionality of this ring.
So give me a second for that. So this is the log of the size of A, but in real life we want to optimize over a continuum set of auctions of prices of whatever. So what do? And here we appeal to learning theory that tells us, well, some well-structured sets behave in this sense as if they are finite. So we have a theorem. I've highlighted the only things that are different between here and here. And this says for every set, even an infinite one. And here, instead of the log of the size of A, we take the pseudo dimension of A, which I have not yet defined. Yeah.
Could I question your assertion that in real life we want to use a continuum of
Okay, very good.
prices?
Y-
In
y-
real life, everything is fine.
You certainly can. The things you optimize over, well, they're finite, but they're so big that I want a better bound than log of the size of them. That's the answer to it. Okay, I want something better here than log of the size of the set of all mechanism I optimize over.
Okay.
Good. For tomorrow, we'll get back to many things you're saying today. But,
So, I'm not actually familiar with the term pseudo-dimension. Are you?
yeah, I'm going to define everything in a
Okay.
second. But I want to show you first why I'm tormenting you through several slides of definitions. The reason is it's going to allow us to replace log of the size of A with pseudo-dimension of A, which is actually going to be fairly small for quite reasonable auctions. So what's the pseudo-dimension of A? So here's the definition, and it's a three-part definition that's a bit annoying, and I knew that I would lose you if I would not show you this. So let A be a family of real valued functions, so it's the same A defined over a set X. You don't even need it to be R to the power of N. You can think about it to the power of N if you want. Sorry, no, I was lying there. So, sorry, it's, yeah, okay, good. So, yeah, you can think about this as R to the power of N, sets of valuations, that's fine. Let Y be a subset of X. So Y, you can think about it as, Y is the set of, good. So Y can contain, valuation 1, which is a tuple of one valuation for each buyer item pair, and then valuation 2, and then valuation 3, etc. So Y is a specific subset of X, a finite subset of X. So you can think about it as a list of valuations. And let T be a threshold number for each of these. So maybe, you know, here the threshold is 5, here it's 6, here it's 10. And we're going to say that...
What is the threshold?
Well, I'll tell you in a
Oh,
second.
okay,
I'll
sorry.
tell you in a second. We say that the family of real valued functions A shatters the set Y of samples with respect to the thresholds T if for every subset of Y, Z, so I'm going to say maybe, you know, Z is going to be, let me get another. Does this work? Sorry. Z is this, and whichever others. There exists an auction, a real valued function from this family that on each of the samples in Z gets value higher than the threshold, and on each of the samples not in Z gets value lower than the threshold. So we take a bunch of samples, we set a threshold for each of them, and then we say if whatever, and then I say I want the revenue here to be high, here to be low, here to be high, etc., where high means above the threshold and low means below the threshold. For each arbitrary choice of high, low, high, whatever, you can find for me an auction in the set we're optimizing over that gets revenue exactly in these directions, high, low, high, etc., we're going to say that the set of auctions shatters this set of samples with respect to these thresholds. Okay, that's the definition. Questions about this definition so far? Good. And we're going to say that A shatters Y if it shatters Y with respect to some thresholds. If there exist thresholds, you know, these 5, 6, 10, whatever, such that A shatters Y with respect to them. And we're going to define the pseudo-dimension of the class A as the largest set that it shatters. Yeah?
What is the relation, or like intuition, what is the intuitive relation between pseudo-dimension and basic dimension?
So, VC dimension, you can think about, once I set the thresholds, above, below becomes 0, 1, then it's the VC dimension. The added thing here, VC dimension is defined over binary functions. Mm-hmm. If you take binary functions with a threshold of 1/2, you get the pseudo dimension. And the other way around, we have real valued functions, we somehow have to make them binary, and we say, you know, we actually, if we can make them binary using whichever thresholds in a way that it's shattered, then we say that it's shattered. So that's an explanation for people who know what the VC dimension is. So this is the pseudo dimension, and miraculously, as I've shown you in the previous slide, this translates directly into how many samples, into a sample guarantee and how many samples we need in order to estimate the revenue of all auctions in this bank. So I realize this is a mouthful. How are we doing on time? Most of the remaining time, except, you know, we're going to talk a little bit about related literature, etc., but a big chunk of the related time will be spent to proving for a specific family of auctions that it has certain pseudo-dimensions, so that you can see how to work with this. You know, I can show you the definition, that I can tell you someone proved that this family of auctions has pseudo-dimension, you know, whatever. You learn nothing from this. So I'm going to show you a little bit how to work with this. Yeah?
That's a strange question. It looks like all of this doesn't really pertain much to auctions. It's a statistics.
That is true. We're going to, in a minute, talk about how to prove that a specific auction has this pseudo-dimension, and there are tricks. There are tricks that are shared by, so the revenue functions of auctions behave in certain ways that there are tricks on how to prove this for them, but to answer your question more generally, yes, we need to understand basic statistical learning theory in order to do revenue maximization from samples. That's, you know, just like for Sergey talked yesterday, you needed to understand what the first order stochastic dominance is or what random
No,
variables are.
I
You need
agree,
to-
but
yeah.
I think these tools could work equally well.
That is correct.
Mm.
Tomorrow we're gonna do something that's more fine-tuned. But even now, the proof I'm gonna show you in a second is gonna exploit specific structure of vector assumptions. Yeah.
Please, the question that's good. Can we think of the mechanisms as just a pricing algorithm? So if we think of Amazon, how to price a book, is that an example of an element of A?
So, pricing a book at 3 and the remote at 6 and this at 5 and this at 7, that's an example of an element of A, but there are much more complicated elements of A. A could also contain, you know, do a second price auction for the bundle of both of these and sell a lottery ticket for this, and everything Sergio talked about yesterday, which we saw was, you know, very, very rich. So depending on the class of things you optimize over, this could be anything. For some of them, we know the pseudo dimension is infinite. For some of them, we know how to bound the pseudo dimension. Let me give you an example. So,
Do you want to get a little bit of
intuition.
sense, yes?
So-
why this
so-
is- I mean, why
So-
really the fact that, you know, there's a law, the larger is the set that shatters,
So to some extent, to some extent, if A shatters Y, it means that there exists a Y such that, you know, let's fix the thresholds for a second. It means that there is a Y that for any choice of up, down, you can make do. It kind of says unintuitively, the number of degrees of freedom you have is at least the size of Y. Otherwise, you wouldn't be able to do all of this. So you can think about the pseudo dimension as the largest number of degrees of freedom as defined in this way.
May I
Yeah.
try another way to look at it? Suppose you have mechanism that's given by 10 real parameters, right? In your mind, the dimension is 10. Now, if the mechanism is really sort of a threshold kind of the way it uses a parameter, your pseudo dimension will be 10. But maybe the way you use your parameters of the mechanism is more complicated, right? Maybe it goes up and down and so on. So if it goes up and down, maybe it's going to be 20. You're going to get maybe 2 that's the weight of 2 for each real dimension, if you will, right? So basically, the pseudo dimension is a way to convert the dimension in our head, which is the number of real parameters, to the actual number of, if you wish, of bit equivalent that you have in each one of these real parameters. Okay? So it's basically always going to be the number of parameters times a little bit, and that little bit depends exactly on what you're using it for, on the revenue function of the auction and so on. Okay, so that's the difference.
Oh,
You don't agree?
I mostly agree. I mostly agree. Yeah, it's slightly more complicated than that, but that's good intuition. Yeah.
Could you define up and down again?
Here.
Yeah.
So up means I want the revenue to be above this threshold. Down
Right.
means I want the revenue to be below this threshold.
Below 6.
Here it's below 6, here it's above 5, here it's below 10, depending on the thresholds. So this says the pseudo dimension is the largest finite set of samples, the size of the largest finite set of samples that is shatterable with respect to some thresholds. Right?
How many thresholds are there?
Sorry?
How much thresholds are there?
So for each sample we give a threshold. And then for each, the exercises with respect to these thresholds, for whichever combination of the 2 to the number of samples combinations of I want this to be high, this to be low, this to be low, this to be high, etc., etc. For each of these, I can find an auction that's compatible with that. Okay. Yeah.
Have you limited A to be finite in the mechanism?
I have not.
Then what guarantees that the largest shatterable set will be finite?
It could be infinite. It could be infinite. Yeah.
So I'm not familiar with the term shattering. Are we talking about partitioning of space?
Shattering is exactly what's the point. Yeah.
It seems trivial that pseudo dimension of 1 is possible. That's trivial.
Mhm.
But at the same time, so if I understand what we did before, we want the pseudo dimension
Yeah. So we need to prove, and we're gonna prove soon, that the set of all separate pricing options have a low pseudo dimension. We're gonna prove that. Okay. Some examples, if A is finite, turns out it's not a hard proof, but I'm not gonna do it, that the pseudo dimension of A is less than the log base 2 of the size of A. But this is for arbitrary A. Many times we can get much better threshold, guarantees. And another example that's actually going to be useful later, if you take as A all affine functions over Rn. So each function is defined by n plus 1 numbers, which are the coefficients. That's not nice. This should be n plus 1. The pseudo dimension is n plus 1. So this is compatible with the intuition that Noam gave you. There are n plus 1 parameters here. These are the levers you can pull, and the pseudo dimension is precisely n plus 1. And this is the number of degrees of freedom. And this is, as we said, this is how we use it. So I'm going to prove to you the following theorem due to Jamie Morgenstern and Tim Rothgarten.
Can you go back? What was the theorem?
That's the theorem we saw earlier already. I just copied it again here.
Oh, so this does not have dimension here.
This has, so we had this slide earlier where I said this is the finite version that we proved. And this turns out to be an infinite version that uses pseudo dimension. So the only thing I change from here to here is instead of log of the size of A, I write pseudo dimension of A.
Okay.
And then again, after I define the pseudo dimension, I pasted this here again. So then you've seen this.
Yeah.
So in order to utilize Moshe's beautiful result of the 1/6 approximation, I want to prove to you that the pseudo dimension of the set of all separate item pricing mechanisms when viewed as a function from valuations to revenue is O of n log n. And here's the point where I slightly disagree with you, Noam. Separate item pricings, we have n parameters. These are prices. According to your explanation, each of them flips once. And still, the best upper bound we have is n log n. We don't know, I don't know how to bound this by n. So we have more stuff kicking in rather than only switch back and forth. So that's the only
The
asterisk.
revenue function is not really linear, but it has a clear geometry.
Exactly. So that's the asterisk I would put over this. You need to be careful when you use that intuition in order to formalize. Other than that, I completely agree with your intuition. So this is what we're going to prove. We have enough time to do this. Good. And again, recall Babayev, Imolika, Lucier, and Weinberg proved that when m equals 1, when we have only one buyer, the better of the optimal separate item pricing and optimal bundle pricing attains at least 1/6 fraction of the optimal revenue, as Serge called it yesterday. The G4 of this class is 1/6. Therefore, this above theorem will tell us that if we take a number of samples that form polynomial in n and h and log of 1/delta, it suffices for learning, for example, an up to 1/7 optimal mechanism. What do? You take sufficiently many samples, you take the empirical better out of the empirical best separate item pricer and empirical best bundle pricer. You're guaranteed that this will give you an approximation that's close to 1/6. Here the epsilon that I chose is the difference between 1/6 and 1/7. Note, if you were really careful, you would tell me, well, this shows that you can optimize over separate item pricing without overfitting. What about optimizing over bundle pricing? And I will tell you, just like Sergio did yesterday, bundle pricing, what does it mean? It means you take all of the items, you put it in the sack, and you say this is a single item that I want to sell to you. So this actually implies low pseudo dimension also for bundle pricing. So this is the only thing I need to prove to you.
Yeah, we have independence across items. So selling separately, why can't I just handle one item at a time, and then for one item I'll get a constant, and then for n items I'll get n. Why do I need to lose another factor of log n
Um, because they play with, let's take this offline, because they play with each other in direct space.
They do.
Yeah, they do. Okay, so let me give you the proof. I'm gonna prove it for m equals 1. If we have time, I'm gonna hand wave to you why it holds for m greater than 1. It's essentially the same proof with more details. Fix samples v1 through vs, and fix, this is gonna be the set capital Y. Fix the thresholds t1 through ts. These are gonna be the thresholds.
M is N, right?
Sorry?
M is N.
M is n.
N is the number of items.
N is the number of items, M is the number of buyers.
Okay.
Oh my God.
Why? Because many things I do with a single buyer, and I like N to be the thing that I'm consistent throughout this presentation. So this is one buyer, so fix samples v1 through vs, fix a threshold for each sample. How big can we make S while keeping this set of samples shatterable? So give me a very big set of samples that is shatterable with respect to some thresholds T1 through TS. I'm going to spend the next slide bounding the size of this set because it is shatterable. This is going to be the only slide for this proof. So it's going to be, we're going to spend some time here, but I promised you eventually there will be a blue rectangle here at the right corner at the bottom. So fix some item I, item number 7. In your mind, think about the price of that item being 0, and think about what happens when you slightly raise this price. And keep track for each such price for at which samples this item gets sold or doesn't get sold. What do I mean by that? I start with a price of 0. At a price of 0, at any of these S samples, this item will be bought. So I put 1, 1, 1, 1. 1 indicates item is bought. I raise the price of this item. I raise it still, at all of the samples that is bought. At some point, at one such samples, maybe more, this price is already too high for the valuation of this specific sample. So this is going to be the new vector of which samples buy the item and which don't. And then I'm going to keep on raising the price of item I until another sample, finds this price too high. And another, eventually I reach the all zeros vector. I might have jumps, right? If two samples have the same valuation, we might skip this. That's fine. At most, there will be S plus 1 such vectors, such which samples buy item number I labelings. Maybe less if we had jumps, but at most S plus 1. Which means that for all items together, this was an experiment for raising the price of one item. For all items together, we're going to have at most S plus 1 to the n huge vectors of which samples buy which prices, which items at the current price. Okay? And I'm going to think about these labelings as kind of intermediate labelings of these samples. You'll see in a second what I mean. So I'm imagining now each sample for given fixed prices, each sample labeled by which items it buys. So fix a specific one out of these S plus 1 to the n, which samples buy which items labelings. So for item I, we have whether sample 1 buys it, whether sample 2 buys, etc., until when sample S buys it. I'm claiming that if we only focus on prices that induce this label of which sample buys which item, the revenue is this function, right? If we know which sample buys which item, the revenue from a specific sample that is so labeled is sigma, and I sum up only the prices of the items that are bought. This is a linear function, right? If for a moment I only think about prices that induce a specific which samples by which items label, this is a linear function. Meaning that its pseudo-dimension over these labels is n plus
You mean linear in PI for fixed L?
1. No, it's for each each sample has its own L's, right? This
Right.
which samples by which items labeling is a huge labeling that labels each sample with separate L's.
Mm-hmm.
So it's linear in the prices, which are the auction I'm optimizing over,
Right.
and in the L's, which label each valuation. So this is exactly, each evaluation is labeled with a
But you think about L as fixed now.
as
You
fixed,
understand
because
that,
I'm
and
only
it's
I'm
linear.
imagining a world in which all of the prices induce a single which samples by which items label. So each sample is associated with its own L's, and each auction is associated with its own P's, and the revenue of a specific auction from a specific valuation is a linear function just as earlier. The prices are the coefficients of this linear functions in these labelings that we have fixed for each of the valuations separately. Different valuations, one valuation, if you, in it, you know, that buyer buys items P1, items 1 and 3, the revenue is P1 plus P3. Another label, the buyer buys items 4 and 6, is going to be P4 plus P6. So it's a linear function of these L's, which, you know, each valuation has, and these prices, which each auction has. So if our world, if we started with valuations actually being labeled like this, you know, we thought about our samples as being samples of these, this pseudo-dimension would have been n plus 1, because I told you earlier that a linear function has pseudo-dimension n plus 1. So this means that even if all the prices induce this labelings, and here I'm going to appeal to a higher, to a very strong lemma by Perlis, Sawel, and Shelach that tells us that it asks the following question. If I have a function with pseudo-dimension n plus 1, and I have S samples, how many high-low labelings, you know, with respect to the thresholds that I fixed, could be induced by this function? And it turns out that the answer is, at most, number of samples to the n plus 1. So what we're saying is that even if all prices induce the same which samples by which items labeling, we would have at most S, number of samples that we took, to the n plus 1 different high-low combinations, possible combinations for given thresholds. But we have many, many, many which samples by which items labeling. So at most, since the overall number of distinct which samples have, so the overall number of distinct which samples have high-low revenue, you know, these high-low labels with respect to the thresholds, is the number of which samples by which items labelings that we have, times for each of these can induce at most S to the n plus 1 different. For each of these auctions can induce at most S to the n plus 1 different labelings. So this is the overall number from all of our auctions, different high-low combinations that can be induced over S samples. And since we said that the set we started with, V1 through Vs, is shatterable, we have that 2 to the S, which is all the possible high-low combinations that you can get, and you know it's shatterable, so all of these you can really get. It must be less than the overall upper bound that we have found on the possible, you know, which samples have high-low revenue labelings. And this tells us that S is of order at most n. So you can see that it's, so back to your question, you'll see. Turns out that many auctions, much more than only these, are kind of linear over areas. Here it's you know, the area is all of the, is a set in which that maintains this label. You know, there are jumps, but the revenues are linear over areas. And the pseudo dimension is quite comfortable to bound for functions that are linear over areas. So that is the thing that makes this appealing to auctions, you know, beyond being general learning theory. Questions about this?
Where's the lowest?
Sorry?
Where's the lowest?
Here it is.
So could you explain again where the two multipliers come from? S plus 1,
Yeah.
S plus
So S plus 1 to the n is here. It's the number of intermediate labelings we move to. S to the n plus 1 is this one. It's for each intermediate labeling, even if all of the prices induce that one, what would be the possible number of distinct high-low combination labels?
And the intermediate labeling is the 1111.
It's
like one of those.
one of those, but this is for one item.
Yes.
Intermediate labeling is one of those for each item.
Yes, okay.
So really what this says, you know, if you take a high-level view of this, it says we have S plus 1 to the n labels. Each of these, if we fix it, the revenue function is linear. Linear functions, we know how to bound the pseudo dimension. We have many of these, so we have to count how many. Be careful, you know, with these jumps. You know, the S plus 1 argument here is crucial. And so we have another factor. Luckily, it's not horrible. You know, this additional factor of S plus 1 to the n, if you squint at it, it's actually very similar to the S to the n plus 1. So it's, you know, it doesn't kill us. I think I actually have a few minutes to hand wave to you why this theorem holds for more than one buyer. So what I'm going to do, I'm going to separate sell the items, each of them using an optimal second price auction with an optimal reserve for that item. So what's going to change? Actually not much. So here I need to be careful about the labelings. At each item, I'm going to have 3 possible labels, not 2. So it's either going to be the label 0, which is doesn't get sold, the label 1, which is sold for the second highest valuation, and the label 2, which is sold for the reserve price. So I'm going to start with 2, 2, 2, 2, 2. If the price is 0, everything gets sold for the second highest valuation. Yeah, sorry. 2 is second highest valuation, 1 is for the reserve price. So everything starts 2, 2, 2, 2, 2. It means everything if the price is 0 gets sold for the second highest valuation. As you increase the prices, as you increase any specific price, at some point, it will start getting, you know, for a specific value, for a specific sample, it will no longer be sold for the second highest valuation. It will be sold for the reserve price, because the reserve price is now sandwiched between the second highest and highest valuation. And after the price passes the first valuation, it will not be sold at all. So here you have 2, 2, 2s, you know, each 2 becomes 1, then becomes 0. So you can see, you can get a similar bound, but so now for each of these, which samples buy which items, and which of these is at the second highest valuation, which of these is at the reserve price. This function is slightly more complicated. It's a linear function, not only of the LIs and PIs, but also of the second highest valuation. but it's still linear in the sense that you want it. None of the terms is quadratic in the sense that would ruin this analysis. And the continuation is quite similar. So it's you know, it's starting to think about how is this still linear and this, I wanted to save it to you, but it's, I'm not hiding anything crucial.
And the dimension is the same.
The dimension is it's is it the same? It's the same, yeah. Eventually it's the same. It's still order and not different parameters hidden in the O. Going back to our previous. No, here I actually think it makes more sense, but it's yeah. So going back to economists, actually, I should practice what I preach. What this says is the pseudo dimension of the set of all separate item pricing when viewed as a function is less than 1,000 times a Magen or 1 million, or I don't know. There is some constant that you can put here instead of the O. The reason I spelled it out in the other thing is once you have other this doesn't have quantifiers. So if I put O here or C times, it's the same. When you have many quantifiers like we had then, for every there exists, for every there exists, if you put these O's, then things start getting, not very readable, at least for me. I don't know, maybe some other people here are better. So, yeah.
Maybe I'm to show my ignorance, especially my lack of understanding.
Or it might show mine. We'll see.
So there was a discussion before that this is kind of a statistical.
Mm-hmm.
So, but it's not in some. I think so. In some important sense, because you don't view the whole sample, you just view, right? So the question is whether you end up, right, viewing the whole sample, or you just view the maximum element, and you have to base your learning on that.
I'm not sure that I follow.
So
Let me say something
so
that
maybe
might
this is
might
my
let me say
understanding.
something that might answer this. If not, ask me again. So one thing, the approach that we took here, maybe that's what you mean, is very wasteful. In the sense that we said, let's estimate, up to very good precision, the expected revenue out of every single possible auction that we're optimizing over. This is a harder thing than saying, let's find a one with good, high expected revenue. There are actually papers that show that in some settings this needs more samples than just identifying the best one. I did this because I wanted to show you general things and not specifically tweak things. Tomorrow we'll not do this, but tomorrow we'll dive into less general things.
Can I try to?
Yeah, please do, please do.
Okay, so when you're trying to optimize for example, the naive approach would be, let's take a sample, find the optimal mechanism for that sample, and let's hope it's going to be good as the original distribution. The point is that generally would not work because there are too many mechanisms. So the dimension is too high, and you can see a very simple example when it won't work, even if you're selling one item to two bidders. So if you get a sample of many pairs of values for bidder one and bidder two, you can always, if you try to optimize a mechanism just for that sample, you can always get all the revenue. Because, these guys are sort of independent. You can learn from one exactly what the value of the other on your sample. So if you optimize for your sample, you will get nothing on the true distribution because it's complete overfitting. Okay? So you can't just optimize over all mechanisms. The trick here is you always need to start by finding a subset of mechanisms that is good enough. And in our situation, the Babayas et al. Paper gave us that thing, and I didn't prove anything there, just quoted. If you just look at selling separately, this is good enough in a weak computer science sense of getting 1/6 of the revenue. But hopefully sometimes you get a subset, Myerson kind lemma, that if you look only at the fixed price mechanism, that is good enough. And if that subset that is good enough, has low enough dimensions, then you're all set. So the trick is always to identify a good enough subset of mechanism and show that it has good, so there are like two theorems. It's good enough in the sense that if you optimize over them, you get good revenue. one.
Okay,
Yeah?
no,
On the other
I'm
hand,
gonna
it's
ask
a
you to
small
stop here.
dimension.
I'm gonna ask you to stop here because I have a slide in 2 minutes that, give me, okay. So I have 2 more slides for today. One of which is, so, you know, what I covered today, I'm gonna call it, very generally speaking, parametric learning. We have a set of auctions, you know, we understand the structure, there are a few parameters we tweak, could be the prices, could be something else. How do we learn these without overfitting? So I'm gonna give you some further reading. There are many beautiful papers that are not here, and we're gonna do a recap, and then I'm gonna lead to what will happen tomorrow. So you can think about pseudo-dimension for other auction classes. In the same paper, they studied the pseudo-dimension of various other auction classes you heard about. You have a different paper in which they say, well, in a single item setting, what we really would have liked to show is that Myersonian auctions, you know, the ones that compare virtual values, etc., have a low dimension. That is not true. They actually have very high dimension. But if you discretize them, then you can get a set that's on the one hand rich enough to still attain up to epsilon optimal revenue on each possible distribution. On the other hand, has bounded pseudo dimensions. So they do this. They you know, discretize this existing class. You need to carefully discretize it. It's not obvious how you do that. This is the paper I told you is relevant to what we're talking about. You can talk about other standard learning theoretic dimensionality. There's beautiful work by Ellen Vittersik and her advisors using Rademacher complexity, you know, similar ideas with, you know, piecewise linear, you know, revenue functions, but you know, you can do more things with this. There are even dimensionality notions specifically developed to be convenient for auction theory, for analyzing auctions. So there's what Vasilis Serkanis called the split sample growth rate, which is a new sample, you know, a learning theoretic dimensionality notion that is very, you know, gives you very good guarantees specifically for auctions. Everything I did today, I did not assume independence at all. The only place we assumed independence of the valuations is to apply Moshe's theorem that gives 1/6. The analysis I give you with the pseudo dimension did not need that at all. There is a beautiful paper by Yantai and Kostistas Kalakis that they find a way, you know, VC dimension-ish, pseudo dimension-ish, to actually give better guarantees because of independence. This is
So
beautiful.
this is the n-log n from the result of Jamie and team is for the correlated case. That's why
It's
you
even
didn't
for the
want to
it's even
separate it.
it's even for the correlated case, yeah.
Okay.
And it's unclear how you would use independence, and they find a way to use independence. There is also non-dimensional analysis. You know, you don't use any dimension. You do things more manually, but still parametric in the sense that you assume structure for the auctions you maximize over. Specifically for the single item case, you assume you know, something related to Meyerson's auction. So there is unbounded valuations. That's a whole different literature I'm not going to talk about. There are, you know, specific problems there. You need some tail assumptions. Otherwise, there's some, you know, very, very high price with very, very tiny probability that you're going to miss regardless of how many samples you take. So this, you know, this is its own literature. You can talk about bounded valuations. One thing we completely didn't talk about today is how you do the optimization. So I proved to you that if you take S samples, you have sufficiently enough information that if you had a powerful computer that could exhaust over many different auctions and calculate the expected revenue for each of these, you know, with separate pricing, it's actually not very hard. But with other auction classes, optimizing over all of them it's unclear how you do that. So there are papers that say, you know, we actually want guarantees that also give us an efficient algorithm to calculate an auction from prices. And there's even some papers that talk about non-truthful mechanisms, and we have bid samples. We have sample from equilibrium behavior. And there's, I'm highlighting this because I think if you need to read one paper and jump to the state of the art, it's a very hard paper to read. But this is a paper that gets tight sample complexity bounds for the single analysis case. By tight, I mean they get the precise polynomials They have upper bounds and lower bounds using Hale divergence. Hard to read, but you know, beautiful paper. Somehow this is the pinnacle of all this single dimensional analysis, all the Myersonian analysis from samples. And a high level recap, going a bit to what Noam said, and we have exactly 3 minutes for this. So Bayesian revenue maximization from samples is ubiquitously seen as exactly, you know, the next step beyond Bayesian revenue maximization, exactly what Noam says. First, understand find a set of auctions that is well structured and gives you some guarantee, like the 1/6 guarantee. And then somehow show that it's, you know, low dimensional, so you get no overfitting. And really the literature has progressed like this. For single item we have, you know, Meyerson's optimal mechanisms. They are very well structured. And then there's some papers that say, well, let's see how we do this from samples without overfitting. Again, a lot of hard work to make it happen, but that's the general idea. And they're multi-item. If you're interested in some percentage, this is getting told what you were interested in. You know, 1/6, 1/10, 1/50, 1/56, I think there was even a paper. There are some, as you learned from Sergio yesterday, the structure of optimal multi-item auctions is horrendously complex. We don't understand it. There are some beautiful papers that say there are some nicely behaved, this is the paper I talked about before, Moshe's paper, there are nicely, you know, structured classes of auctions that give you guarantee a constant fraction, some fraction of the optimal revenue. And then there are beautiful papers, this is the Morgenstern-Rothgarten paper we talked about, that show if you optimize over this class, you will not get overfit. What about the up to epsilon, which is what you were interested in? Because again, you know, it's, while I'm perfectly happy to solve a algorithmic, you know, design problem, find an algorithm that's, you know, runs up to 6 times slower than the optimal. I'm not sure even what that means, but if I could do that, I would say problem solved. Revenue is not running time. I do not know many sellers, you know, and I say this with the utmost respect to your beautiful result. I don't know many sellers that I would tell them, you know, I have a beautiful mechanism that would get you 1/6 out of what you could have gotten otherwise. I don't know many sellers that would have jumped at this, you know, price. And this is what's
the wrong interpretation of the mechanism. So the interpretation is, you know, you have a seller, let him pick a mechanism, then compare to this mechanism of selling separately in bundle. If you get lower expectation for his original mechanism, he should toss it. If he gets better expectation, he knows that his mechanism gives at least 1/6.
Okay.
And he should run his own mechanism.
Very good, but it still doesn't tell him how to find his own mechanism. That's it. No, but I agree. I'm saying now things a bit dramatically in order for the computer science students in the audience to shift them to a slightly different state of mind. As I said, you know, this is one of the most beautiful papers that I know. So up to epsilon, Sergio told you, even for one buyer, 2 items, additive, independent, we don't know. Some distributions, we know something, some distributions, we know infinite menu size, all the things Sergio talked about. Generally, we don't know. So how about from samples that come up? Why bother when we don't even have the Bayesian case? We actually know that up to epsilon, you know, mechanisms have very, very high dimension. You pick the dimension type, they have very high dimension. So you know, why even bother? So this calls, if it's even solvable, this calls for approaches that do not rely on the auction structure, what I would call non-parametric learning. Approaches that do not assume we're optimizing over nicely structured auctions, and this is precisely what I will be talking about today.